Okay, this is lecture 6.1, and it's mostly about things that should be reviewed for you, which is Lewis structures and how to write them. I am going to add some information that you probably did not learn in first year chemistry, but we definitely need to make sure that you're good at drawing Lewis structures and some of the vocabulary that goes with them. So as usual, please, before you watch the rest of this video, make sure that you've completed a framework of learning target notes in your notebook. When you're finished with these, then you can come back and watch the rest of the video. So stop the video now and restart it when you're ready. Okay, so let's get started. Lewis structures, remember, are the pictures or the sketches that show us the basic arrangements of electron pairs around the atoms inside covalently bonded molecules. So we have some that are shared, which would be bonded pairs, and then we have some that are not shared, that are pretty much not stuck between the nuclei of two atoms, and so they are our lone pairs or our unshared pairs. So there are some basic rules set up that your textbook sets up for you for drawing Lewis structures, and this is a basic summary of them. You should already have these in your notes with some space for examples. So I'm going to expand on these a little bit individually, and then we'll do a bunch of examples together. So the first thing that you see is that you're going to need to make some decisions about, when you're seeing a formula for a molecule, which atom belongs in the middle. So typically this is fairly straightforward at the level that we do, and we don't do rings and we don't do squares, and so we usually have one central atom with a number of atoms attached to that atom directly. And so because electronegativity is a really important piece in covalent bonding, the electrons will usually be attracted away from the center of the molecule, because otherwise we're putting electrons into smaller spaces and their repulsions make that difficult. So the idea is that usually your central atom is the least electronegative, which would be on your periodic table, if you're doing it the quick way, the farthest from fluorine, okay? Or it may be the one with the lower group number. That's also going to put it the farthest from fluorine. Or it's going to be the one that in the formula there is only one of. So these are some ways that you can tell, and we'll talk about that as we do the examples. The next thing that you need to do is determine how many valence electrons you have to work with, and how many valence electrons will have to be shared by all the atoms in that molecule. We don't worry about which atom brought the electrons. We only worry about how the atoms together distribute the electrons, and which ones end up attracted between nuclei and which ones end up pretty much owned by individual atoms. So we need to add up the total valence electrons. Remember quickly, this is that the A group number, or the Roman numeral, tells you the number of valence electrons. Also remember that if you have polyatomic ions, you have to add electrons to account for the negative charge, and you have to subtract electrons to account for the positive charge. And again, we don't really care where they came from or which atoms they're attached to. They're really just a part of the whole molecule. So I always kind of picture a polyatomic ion as a little band of thieves going out to look for electrons to steal. So anyway, the next thing that you'll do then will be to connect everybody to the central atom with single bonds. Remember that single bonds are shared electron pairs. So a single bond accounts for 2 valence electrons, all right? And then the book tells you to add up how many you've used and subtract it from the total number. I don't really do that. What I really do is start counting, and I just count by 2s, whether they're shared or unshared, until I get to the total number of valence electrons available. So you'll see when I give examples how that changes a little bit. You can do it either way. After I've put single bonds on every atom so that they're all attached to the central atom, now I'm going to start distributing electrons to account for the octets that these atoms will need. There are some exceptions, I'll talk about them in a minute, but you definitely need to start always by adding lone pairs of electrons to terminal atoms. All right, so once you've bonded the terminal atoms, now the terminal atoms are the not central atoms, you want to start adding lone pairs to the terminal atoms to provide octets for them. Please remember that the only terminal atom that does not get an octet is hydrogen. Okay, hydrogen has only one energy level. Hydrogen can share only one other electron. It doesn't have space for more, so hydrogen will have one bond and that's it. No dots, no unshared electrons, never multiple bonds. okay? After you've distributed octets to your terminal atoms, if you still have more to draw, then you're going to add lone pairs to the central atom. And we'll talk about how that works to be able to expand the octets. It won't always mean that you have expanded octets. It may expand the octets, and so we'll talk about that as we look at the exceptions. All right, so there are some exceptions, and you want to think always, put lone pairs of electrons on terminal atoms first. If you have extras, put them on the central atom. If you don't have enough, we'll talk about what to do with that in a second, but you have to be careful because some of our exceptions allow fewer than 8. And so the ones that are electron deficient are like group 1, group 2, group 3. Group 1 doesn't usually make covalent bonds, but group 2A and group 3A might, especially beryllium and boron. They're pretty electronegative. So if you have beryllium or boron as a central atom, either one of those will have fewer than 8 electrons when they're finished in most cases. Sometimes aluminum shows up here as well, but it's typically beryllium and boron. So remember, please, that boron's stable or satisfied when it has 2 covalent bonds, which is 4 shared electrons, and that boron is satisfied with 3. Also recognize that if you have an odd number of electrons, the odd number is usually going to be because of nitrogen. And so if you have an odd number and you don't have enough electrons to make even pairs, then make sure that you put the lone electron or the odd electron on your nitrogen center, and it would just be a single dot. I do also want to talk about expanding octets. And so when we expand octets, remember that we talked about this with electron configurations, that nonmetals from period 3 or higher can expand their octet and may actually expand to hold up to 10 or 12 electrons. They will be in pairs, and these will be the ones that if you have extras and you've added your terminal atoms octets and you've added the octet on the center and you still have more to draw, you're going to put them on the center, and then you're going to verify that they're actually one of the ones that are allowed to do that. All right, so that's your idea of distributing electrons. And then you're going to count total electrons, and if you actually don't have enough electrons to give everyone, including the central atom, its octet, and they're not exceptions, then you're going to start moving lone pairs from the terminal atoms to make them bonds. So you'll move them from being on just the outside of the terminal atom to being a shared bonded pair, which is the dash in between the atoms. There are a few things that you have to remember. You're only going to do this as a last resort. Don't start making multiple bonds just because you like them, okay? So only if you've drawn all of the electrons that you can draw and everyone doesn't satisfy the octet rule or their exception, then you start making multiple bonds. Also remember that hydrogen cannot form multiple bonds, so if you think you're multiple bonding to hydrogen, you've got a mistake somewhere. Also remember that we'll never share more than 6 electrons between 2 atoms, so we'll only ever form double bonds, which would be 4 electrons, or triple bonds, which would be 6 electrons. All right, so double bonds are 2 lines and triple bonds are 3, like so. And then finally, sometimes you don't need to put a double bond or a triple bond in every space available. So we end up with something called resonance structures. And this may be new for you. So really read carefully the section in the book about resonance structures, but recognize that resonance structures are a multiple bond that really does not exist only between those 2 atoms. It's really electrons that are what we call delocalized around the center atom. They're not really stuck between the central atom and one, or the central atom and another terminal atom. And so they end up being kind of structures that are, they have different bond energies than you would expect. They have different bond strengths than you would expect. And this is because, remember from what you learned in 5.5, that the single bonds have a bond order of 1, double bonds have a bond order of 2. But let's say you had a resonance structure that looked like this as your Lewis structure, and you could have put this double bond here, or you could have put this double bond here, right? Then what happens is that this is what we truly call resonance, and we can draw them both, and we can say that that extra pair of electrons really is just kind of around that central atom. It's not really in one place or the other. We just have to choose one place or the other to draw. So they're delocalized. If I were going to do that, I would be averaging this. So rather than this being a single bond or two single bonds or being two double bonds, this is really like a single and a double averaged, which would be a bond and a half. So just kind of think that that's going to be somewhere on average in between the strength of a single bond and a double bond, or in between the length of a single bond and a double bond. So kind of keep that in mind. All right, so let's do a few examples so that we can talk about some of these exceptions as we go, and you can kind of see the pattern. I'm going to determine the central atom first. So for H2S, I know H can't go in the middle, which means that I have sulfur in the middle and two hydrogens. And I'm going to add up the total valence electrons. So hydrogen is group 1. There are two hydrogens with 1. Sulfur is group 6. So that gives me a total of 8 valence electrons. I'm going to start with single bonds, and that counts as 4. I have 2 in each, so 2, 4. And now I'm going to add to the terminal atoms, except that hydrogen doesn't get them. So instead of adding to the terminal atoms, I have to add to the central atom until I get to 8. So I have accounted for right now 2, 4, and I'm going to add 6, 8 on my central atom. And now you can see that I have total of 2, 4, 6, 8, which matches the 8 I'm allowed to draw. And so everybody has their octet. We can check that. Sulfur has 8, 2, 4, 6, 8, and each hydrogen has only 2, but hydrogen's stable with 2, so it's an exception and we're good to go. All right, so let's do another one. BCl3, the boron is going to end up in the middle. This is because boron is much less electronegative than chlorine. It's in the lower group number, however you want to set that up. So we're going to set up our 3 chlorines around the boron. I'm going to count up my electrons. Boron is group 3, so it has 3. I have 3 chlorines. It's group 7, so each has 7. That gives me 21, and 3 more is 24 valence electrons to draw. I'm going to single bond the chlorines to the boron, so that accounts for 2, 4, 6. And now I'm going to add electrons to my terminal atoms and see what happens. I'm going to add them in pairs. So that was 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so I've connected everybody. I've distributed the rest. I'm going to check my octets. So when I look at this, I can see that each of these chlorines looks the same, and they each have 2, 4, 6, 8, so we're good. I'm going to come in and check the octet on the boron. Here's a problem. When I look at boron, I see that boron has only 2, 4, 6, but remember that boron is one of our exceptions, and so it's allowed to have only 6. So then the final thing I'm going to do is come back in and check all of the electrons and count one more time. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So my final structure, let me get all of this out of here, is going to look like this. Okay, so I have 24 valence electrons accounted for, and I've set up my structure. All right, let's do another one. NO. Now there is no central atom, so I don't need to worry about that. There are only 2 atoms. They're going to just be set up as such with bonds between them. I'm going to count my electrons. So nitrogen is group 5 with 5 electrons. Oxygen is group 6. And then this positive 1 charge means that together they lost an electron, so I'm subtracting 1, and that gives me a total of 10 valence electrons to draw. All right, so I'm going to start with a single bond. There's 2, and now I'm just going to distribute, pick an atom, one or the other, 4, 6, 8, 10, and I see that I'm done with valence electrons. I only have 10 to draw. I'm going to check the octets, and nitrogen's okay, but oxygen is not. So oxygen right now has only 4 electrons, which means I'm going to need to reassign some of these electrons as the nitrogen has as shared rather than as assigned only to nitrogen. So I'm going to take this pair off and move it to here as a bond. And I can see that that helped a little bit, but that oxygen still only has 6. So I'm going to do it again, and I'm going to, oops, sorry, I'm going to move another pair. Wow, sorry, I'm a mess. And make it a bond. And now I can see that nitrogen has 8, and oxygen has 8. And I can count my total, 2, 4, 6, 8, 10, which is what I'm allowed to draw. So I'm going to say that my structure looks like that. Now this is a little messy. I like to make them kind of symmetrical. So I'm going to actually come back in and move those dots there, but it's pretty much irrelevant. The only other thing I need to know is that I need to, because this is an ion, put brackets with the charge around that, just so that the whole world is aware that the only way that works is if they lose an electron, because otherwise I'd have 11 to account for. Okay? All right, let's try another one. NO21 minus. Now the nitrogen will go in the middle because it's less electronegative than oxygen. And I need to draw 2 O's. I'm going to total up my electrons. Nitrogen is group 5. I have 2 oxygens, which are group 6. And the -1 means this whole group of atoms gained an electron. Sorry. So we're going to add an electron to that. All right. So this is 12 plus 5 is 12 plus 5 is 17, plus 1 more is 18 electrons to account for. I'm going to do the same pattern. Start with my central atom and single bonds. That accounts for 4. Go to your terminal atoms, 6, 8, 10, 12, 14, 16. I have 18 to draw, so I'm going to go ahead and put the other 2 on the center. Now I'm going to check my octets. I can see that the oxygens are okay, but the nitrogen is not. The nitrogen has only 6 electrons. So now that I've drawn my entire structure, all 18 electrons, and nitrogen's not satisfied, I need to move a pair of electrons, and I can choose in this case one or the other. I don't need both. So I'm going to choose to move electrons from here, and that puts that as a double bond. Now I can check, and I see oxygen's octet, and oxygen's octet, and nitrogen's octet. And my total number of electrons is 2, 4, 6, 8, 10, 12, 14, 16, 18, which is what I'm allowed to draw. At that point, I can recognize that I need to put the brackets, need to put the brackets around this because it's an ion and the charge. But you might have chosen, if you were doing this on your own, to draw it like this instead. And technically, those are equal and equivalent structures. So this is a resonance structure situation. Okay, so technically these both represent that molecule, and that extra pair of electrons, that's the double bond, is a delocalized pair of electrons. All right, we'll do a couple more pretty quickly. So SCN1 minus. This is weird because I'm trying to figure out who goes where. Sulfur appears that it would be more electronegative than carbon, less electronegative than carbon. I'm not sure, I'd have to look it up because they're in different periods. So here's where this gives you a hint, or you can use the idea that your central atom will be the one with the lowest group number. Okay, so I'm going to set this up as SCN. I'm going to add up my electrons, 6 for sulfur, 4 for carbon, 5 for nitrogen, 1 more for the negative charge. Gives me 16 electrons to draw. I'm starting with single bonds. You can see the pattern is always the same. 2, 4, add them to the terminal atoms, 6, 8, 10, 12, 14, 16. I'm done drawing electrons. Sulfur and nitrogen are both okay with octets, but carbon is not. So now I'm going to move electrons. And this actually gives me some choices in this case. I can move them from the sulfur and make a bond here. I can that doesn't help enough though, right? because I have, sorry, I got lost in the center of this. So I have only 6 on the carbon now, right? So I need to do it again. I can do it from the nitrogen and make it look like this. So 2 double bonds, and it's an ion, so I could do this. Or I can be a little more creative, and I could do this with a triple bond, and a pair of electrons on the nitrogen, and 3 pair of electrons on the sulfur. Or I could do this with the 3 pair of electrons and the single bond on the nitrogen, and the 1 pair of electrons and the 3 bonds on the sulfur. And technically these are all possible structures. So we'll come back and look at this in a minute to help us decide which of these structures is actually the most likely. Okay, so we'll kind of just go from there. So let's see. Let's do another one. I3 1 minus. This is a central atom that has to be iodine now, so I'm going to draw my 3 iodines. I'm going to add this up. This would be 3 times 7 for each one, plus 1 more for the negative charge, so this is 22 electrons. I'm going to add electrons till I get to 22, so this is 2, 4, add to the terminal, 6, 8, 10, 12, 14, 16. I have way more to draw, so I'm going to do 18, 20, 22, okay? And this gives me 22 electrons. Notice that when I check octets, the outside iodines have their octets, but the central iodine actually is expanded. So I need to check my periodic table and make sure, but yes, iodine would have empty D sublevel spaces. It's in the 5th energy level. So the 5D is empty, and it could definitely do this, and that's okay. So, so because it's okay for iodine to do that, now I'm going to just double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 electrons. Everybody has what they need. I'm going to draw the brackets and the charge, and I'm finished. Okay, so this is like the basic of drawing Lewis structures. The only thing that I have left to talk about with you is something called formal charge, which you already read about. But this is basically the idea of helping us evaluate in something like this situation with thiocyanate, when there's more than one option and they're not all equivalent, because up here they were equivalent, okay, then formal charge helps me to decide which is the most important of those structures, right? So it's basically a calculation that allows us to say that in covalent bonding, if these atoms have one unpaired electron and they pair it in a bond, that would be their most important structure, right? So you can see that beryllium with 2 would form 2 bonds, or boron with 3 unpaired electrons should form 3. This is why those are allowed to have fewer than an octet in covalent bonding. Carbon, though, now we start to pair those up and we get octets. Nitrogen, we get only 3 bonds, but this pair of electrons means it still has its octet. So I would expect that most structures for nitrogen would have 3 bonds and a pair of electrons. Oxygen would have 2 bonds and 2 pair of electrons, and fluorine would have 1 bond and 3 pair of electrons. And of course, neon isn't going to need to make any bonds. So formal charges let us evaluate how close this is, how close our structure is to this, all right? And the way that your book tells you looks like a complicated formula, but the way that I always do it is the same idea, just more simple, which would be it's the number of valence electrons you would have minus the number of dots on that atom minus the number of dashes on that atom. And you do them for individual atoms. So let's come back up here to thiocyanate, where we have some decisions to make, and calculate the formal charges. Okay, so we're going to do them individually. So for sulfur in this structure, the sulfur is group 6, so it has 6 valence electrons, minus dots, so there are 4 dots, minus dashes, there are 2 dashes, which means the formal charge on the sulfur in this case is 0, right? The carbon in this case has 4 valence electrons, and then it would be minus 2, no dots, but 4 dashes, which is also 0. And the nitrogen, oops, let me change colors again. The nitrogen in this case, if we're looking at this, would be 5 valence electrons minus 4 dots minus 2 dashes, which gives us 5 minus 4 minus 2 is -1, right? So the formal charge for the nitrogen in this is -1, the formal charge for the carbon is 0, and the sulfur is 0. Most important structures usually have formal charges that are all 0. So often we don't have to worry about it, and if we don't have choices, we can't worry about it. But now I need to see evaluate what happens over here. So we're going to do the same thing over here. And the sulfur, again, has 6 valence electrons minus 6 dots minus 1 dash gives me -1. The carbon has 4 valence electrons minus no dots minus 4 dashes, so it's 0. And the nitrogen has 5 valence electrons minus 2 dots minus 3 dashes, which equals 0. So you can see the formal charges are different. We'll do it again for the final structure. Sulfur would be 6 valence electrons minus 2 dots minus 3 dashes, gives us +1. Carbon would be, again, 4 valence electrons minus 0 dots minus 4 dashes, so it didn't change. And nitrogen would be 5 valence electrons minus 6 dots minus 1 dash, gives us -1. All right, so you can see that we would like the formal charges to always be closest to 0, right? But none of these have all formal charges of 0. So as we're doing this, we are going to have to evaluate which of these structures is better. I would say that this structure is not really an option. This would be because there's 2 that are not 0 instead of 1. So I'm going to ignore that structure for right now, and I'm going to look at the other 2. All right. When I look at the other 2, I need to remember that the most, let's come down here so you can see it. The most important Lewis structure is the one in which the formal charges on all atoms are 0 or closest to 0. And if not, the negative formal charge falls on the more electronegative atom. So when I look at this, if I'm comparing electronegativities, nitrogen is one of the most electronegative atoms on the periodic table. Sulfur is in the next period and is less electronegative. So I would expect that I would want my formal charge of nitrogen to be the one that's the -1 here, versus in this structure, sulfur with the value of -1. Okay, so technically, by formal charges, this structure is the most important. So this is how you use that to evaluate that. We're going to practice all of this in class, so thank you for your attention. Make sure that you bring questions with you to class.